Welcome to a unit called Discrete Mathematics. This video will serve as an introduction to the unit as well as the first lesson of the unit. One question that we would ask in a unit like this is, do you think we would ever run out of phone numbers? And if you think about it, this question doesn't really fit into the type of math that we've studied before. It's about phone numbers and these digits that we use to call people. Okay, well, if you're interested in this question at all, you could look at your booklet. On the front page, there's a map of all of the area codes of the United States. But then if you turn to the very back of your booklet, you'll see just a blown up view of that same map, so you could see some of the area codes a little bit better. And one of the things that we'll study in this unit is the patterns of numbers, as well as just working with numbers in general, making sense of how to answer questions like these. So you could look for some patterns in the map that you see on area codes. One thing that doesn't show up though is the fact that when you call 911, just those three numbers, that wipes out the entire set of phone numbers that relate to the quote area code 911. Think about it. The 7 digits that come after that won't even be considered because it'll already take you to the emergency line. There are other things that happen too, like I don't think the 000 is an area code, and 800 and 888 are used for companies for toll-free lines. Okay, enjoy that visual then. Let's move on. Now, this unit will be different than the rest of the units that we studied. In previous units, we worked with connected numbers or continuous numbers, equations that represent all numbers in the past or in the future. So we'll be working with discrete numbers. What does that mean exactly? Well, the Latin origin of the word discrete is discretus, which means separate. And separate, that means the numbers are separate. We're going to be working with area codes like 512. What does that mean? Does that mean we're including 512.5 or 512.1? No, the numbers are separate. We have different area codes that we're working with. Now, the antonym, the opposite of discrete, is connected. And we think about that when we first learned the number line, that all of these numbers show up on the number line, and there are an infinite number of numbers on the number line. Now, that type of study of mathematics shows up in calculus, and our focus in calculus is about connected numbers, continuity. So this will give you a contrast, this unit, of what would be studied in calculus versus what would be studied in a course like statistics or discrete math. Let's take a look at the difference between those two as a bigger picture here. And so let's see here. We have discrete math over here. The first thing that we're going to study today is basic combinatorics. Our first lesson is about permutations, basically dealing with like how numbers interact and possibilities of things. Then we'll study all of these things in order. We're not actually going to touch on statistics, graph theory, and number theory, but those are things that you could study in the future, like in a statistics course, either at our school or in college. And then all of the courses on the right, all of the things on the right are basically under the category of continuous math. Now, you might not think of it in geometry, especially with shapes, but as far as the coordinate plane is concerned, putting shapes on a coordinate plane, then that definitely does the trick. It fits into continuous math. And then calculus, like I mentioned, these are the 4 main topics of calculus, but we also have basically algebra, trig, algebra 2, and calculus relate all in this continuous idea of math. All right, that's the intro stuff. Let's take a look at the first lesson, which, like I said, is called Basic Combinatorics. We'll be just basically counting in this first topic, and then I'm introducing the idea of permutations to your brain and thinking about what that actually means and how we've kind of already done stuff like that before. Let's start off though with something. Thanks for watching. Bye-bye. I just have some review questions for you. The basic things that we mostly already know about, a deck of cards, a die, which is, if you have 2 die, it's dice, and thinking about a chessboard. The only thing that I don't expect you to know off the top of your head is a contract bridge hand. I've never played bridge. Don't expect you to know how many cards in here, but you could take a guess. So what I want you to do is answer these questions on your own, pause the video, and then come back after you've tried your best, and we'll go over the answers. Okay, pause. And welcome back, ladies and gentlemen. Okay. Hey, I hope you knew that the number of cards in a standard deck was 52. If you include the jokers, it's 54. 52 divided by 4 is 13. If you're holding a die in your hand, you could grab it from any game that you have in your house. There are 6 sides, but you might not have guessed that the number of possible totals when 2 dice are rolled is 11. What that basically means, if you roll these 2 dice, what are all of the possible totals? Well, if you roll 2 dice, you can't get 1. You would get at least 2. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's 9 plus 2. So 3, 3, 3 plus 2, 11. Does that make sense? Okay. Vertices on a decagon. A decagon is just a 10-sided figure, not 3-dimensional, just 2-dimensional. And you could be bouncing between 9, 10, 11. But once you sketch it, which is kind of a challenge, you'll be able to see it. And then a chessboard is 8 by 8. A better question for this would be like how many keys are on the piano or something, but 13 for the bridge hand. But I want you to notice like what your brain was doing when you answered these questions. Hopefully they were just counting, and that's what we're going to do for a little bit here. So let's do it again. Obviously I can't do 3 volunteers here, but what we're going to do is we're going to find the number of possible ways that we could choose 2 marbles from a bag containing 3 marbles. So here we go. We have our red marble, we have our green marble, and our blue marble. How wonderful. Obviously I could have just sketched marbles. Okay, we're going to answer a few questions here. So the first one is, how many different ways can we do this if the order is important? So that's a permutation, but I'll define that later. If the order is important of these marbles, then let's just write out the possibilities. Let's just count, Here we go. So we're doing 2 at a time. We have red, green. We have red, blue. We have blue, green. We have blue, red. And then finally we have some greens that are first in order, green, red, and green, blue. And now we count. Are you ready? Oh my goodness. 1, 2, 3, 4, 5, 6. Yes, we did it. So there are 6 ways that we could choose 2 marbles from a bag containing 3 marbles. Now, all right, let's consider the other situation. The order is not important. Oh my goodness. If the order is not important, then we have, we'll choose red, green, and then we can't have red, green again, so that's out. And then let's choose blue, green, and then we can't have blue, green again. And then we'll choose blue, red, and then red, blue. So for permutation, it's 6 ways. For combination, it's 3 ways. All right, that was an arrangement. That exercise was all about counting and arranging, something that we can all do and we've done for a while. Now here's another one, and we're going to get a visual understanding of what this looks like. How many 3-letter codes can be formed using A, B, C, and D if no letter can be repeated? So how do we do it? And by the way, there are no notes for this. How do we do it? How would you start? Well, I think many of us would just start writing out this A, B, C, D situation. So let's see what that would look like. Wait a second. All right, let's double check. 3-letter codes. Okay, we're not using all 4. All right, the first one is A, B, C. 3-letter codes. First, we start out with A, B, C, then we do all of the A's first. A. Okay, if we've exhausted all those. Basically in the orders, right? So A, B, D is different than A, D, B. And then we do the things that start with B first, and C, and D. All right, and then we could just count. 4 down, 6 across, the possibilities, 24. But perhaps we could see that in a different way. Let's look at a tree diagram. Some of you might start your visual looking like this. I would say not most, but you basically start at a point. This is like your thought. You begin your thought. Okay, how am I going to do this? Well, first I'm going to pick A first. And then I could think about the possibilities that come after A. Well, there are 3 of them. So first there are 4 possibilities. Then there are 3 left. Then there are 2 left. So if you do 4 times 3 times 2, 4 times 3 times 2 is 24 again. Hey, how about that? That's not too fancy. Now that we've reminded ourselves of how to count and how to arrange things, let's get some formal definitions and examples down. The first idea is the multiplication principle of counting. And we need this because when you just list out the possibilities like we just did, it could get really difficult once you start to deal with something more than 5 or 6 numbers. So the very first thing is how we actually use this multiplication principle. All right, and it basically goes like this. There's a procedure that's performed in a sequence of stages. And, it's slots or something like that. And we're going to talk about an example where we think about the possibilities for a Texas license plate. Then each stage can be done a number of ways. Your textbook and many of them call that R. And then the ways are multiplied by each other. At this point, this shouldn't make a ton of sense to you until you see it in action. Now, just a little thing that we have to assume right here, the ways a stage can be done must be independent. What that means is if we're going to draw some cards from a deck, we have to replace the first ones. Otherwise, we have what's called conditional probability, which we'll touch on later, but there's a lot of detail that goes into that and it could get pretty confusing. All right, first principle down. Let's check out the first example, which is about the current Texas license plate. And thinking about how many different Texas license plates can be made with the restriction of 3 letters. Notice 3 letters followed by 4 numbers. Let's think about this. What are the stages or the slots? Well, let me tell you, the license plate has 7 things, 3 letters and 4 numbers. So we have this situation, these slots, 1, 2, 3, 4, 5, 6, 7. Those are the stages. And that's how we're going to think about it too, just in stages. Now, each stage can be done a number of ways. Okay, well, how many ways can we choose 3 letters? Well, let's see. For the first slot, we can choose 26 letters. And the second slot, we can choose 26 letters. So many there are in the alphabet. And the third slot, we could choose 26 letters. Nobody told us we couldn't choose the previous letter. And then, what are all the ways that we can choose a number? Well, there's 0 through 9, so we could choose those for each of those slots. And the multiplication principle then says multiply all of these numbers together, and that's how many different Texas license plates you'll get, which happens to be 175,760,000. Wow, that's quite a few possibilities. 175 million, almost 176 million. It's pretty wild. So it's good, that they have all those different possibilities. And that's only based on the fact that they're not using letters over here. If they use letters and numbers in any way, it'd be 36 times 36 times 36, 7 times, Now, what if no letter or digit can be repeated? That changes things slightly. I don't know why the state would do that. But basically, instead of 26 possibilities, it'd be 26, 25, 24, 10, 9, 8, 7. And that would just reduce the number of possibilities that there are. Okay, well, permutations. What we've just been doing is basically been permutations. It's like your combination lock for your locker, except it's not really a combination lock. It's a permutation because the order in which you put those numbers in matters. So a permutation is defined as the number of ways that a set of n objects, letters, numbers, people, can be arranged in order. And so that set of n objects is called an n set. And I say that because the next bullet point here is that there are n factorial. Okay, this is pronounced n factorial, not n permutations of an n set. And what n factorial means is n times n minus 1 times n minus 2 times n minus 3 and so on. What we did kind of in the beginning, 4 times 3 times 2 times 1. And here's the official notation with just using any number n, so any positive number. And so we don't usually do negative 3 factorial or anything like that, but we could, I guess. And that just basically means we're going to multiply by every digit beneath it all the way down to 1. So if we decided to do only 3 times 2 times 1, that would be 6. So 3 factorial is 6. And that means 4 factorial is 24, which we kind of learned at the beginning of the video. Now, and so you're going to use that, so don't forget that and refer to that. And questions to ask when you're counting is, what's the process? What am I actually doing here? So how can I set up these slots? Does the order matter? Is this a permutation? And what is the first stage? And what's the second stage? And so on. And those stages are just slots in your and with using the multiplication principle. So let's apply this definition to an example. Here it is. How many words can be made with your name? And quote words because they're not actually words, because some of them are just an arrangement of letters. But let's assume that just if you rearrange Sarah's name, that every selection of the ordering of numbers gives you an actual word. Doesn't matter that it's not really a word, okay? And let's think about this whole process. You know, the process that we're doing here is arranging letters. And then the next question to ask ourselves, does the order matter? And in this case, well, we're creating words with our name, so yeah, the order matters, which means it's a permutation. And now I'll just reference the information on the right here. It says the first stage is the first letter and the second stage is the second letter. All right, so we could just write out Sarah. It wouldn't be too bad. Write out Sarah and then switch H and A and then switch R and H and, you know, do all the possibilities for everything starting with S and everything starting with A and R and H and all that. But you don't really need to do that. Let's set up the slots here. All right, let's use our slot method. Here we go, Sarah. If we're choosing letters, we have 5 letters to choose from. And then after we choose S or A or whatever, we have 4 left. And then we have 3 left and 2 left and 1 left. But you might be looking at this and there's a problem. How do you tell the difference between this A and this A? Well, you can't actually, unless you gave it a subscript, A1 and A2. So we're going to talk in a moment about distinguishable permutations. What we need to do here is we actually need to take this total, which happens to be 24 times 5, which is 120. And then we need to divide by what happens with the duplicates. And I'll tell you this and then I'll define it a little bit later, is because there's one letter that's duplicated, we have to divide by 2 factorial. You would see that if you worked it out and noticed the pattern in all these. But let's say that Sarah had 3 A's. You know, there was no R or something. There would still be 5 times 4 times 3 times 2 times 1. But then we would divide by 3 factorial. And again, I think the best way to see it is when you write it out. So if you can actually write that out, you could do that with your own name though. So try to do it with your own name. But for a name like Jonah, you know, you don't have any duplicates, so it's going to just be 5 times 4 times 3 times 2 times 1. Okay. All right. This information could be added just to your definition of permutations, distinguishable permutations. What we just did with that example was we were thinking about what is a permutation, how do we figure it out, but then what do we do if there are duplicates? How do we distinguish between the word Sarah, where the first A is first and the second A is second, versus Sarah, where the second A is first and the first A is second? Really, there's not a difference. So the permutations of an n set would just be n factorial. So like Jonah, 5 times 4 times 3 times 2 times 1. That's the number of permutations of his name. But in order for them to be distinguishable, all of the different words, then what we need to do, and don't be confused by this, we just need to divide by the number of duplicates of certain objects. So let's say your name had 2 sets of duplicate numbers or letters. So you had 2 of one letter and 3 of another letter. Then you just do this like usual, and you would divide by 3 factorial and 2 factorial. Okay? So notice the second bullet point. N sub 1 is the number of duplicates of the first object. So if A is duplicated in Sarah, then we have to divide by 2, the 2 duplicates, factorial. Boom. And then nothing else. This is only listed up to K because if there are like 10 different objects or 20 different objects that are duplicated, and how many times are they duplicated? So most things, like in just our names, are only duplicated once, but if your name has multiple duplicated letters, then you would have multiple things you would divide by. Just a quick example of a word that would have multiple duplication. The word constitution. There are multiple letters that are duplicated in that word. Okay, we are wrapping things up here, and here's a quick summary. Well, it's not really that quick. It's a summary of the ways to calculate permutations. And so you have a spot for the permutation counting formula over here. We really already talked about slots, which is the best approach to counting and figuring out permutations. And so just putting them in the appropriate slot and using the multiplication rule. Now here's the formula. So jot this down. NPR, not National Public Radio, but the number of things taken r at a time is n factorial over n minus r factorial. Right? So those parentheses matter down there. And so we're going to see that on your calculator in just a moment. R is always less than n. And if r is greater than n, then we have 0. It's impossible. One little nugget of information is it's assumed that 0 factorial is 1. And it helps us with some calculations in later courses and upper level courses as well. All right, so this is just the official formula, which is actually in your calculator. And here is how to get that from your calculator. What you'll do is just type the n value that you're working with. So we're going to use some of these as examples right here. Just type that number first on your main screen, and then press math and arrow right to probability. So PRB, and then you'll press the number 2 or arrow down to it. And then it'll pop up on your screen, and then you enter the R value that you're working with. So let's evaluate these ones on your calculator just to wrap things up. So you'll enter that 6 first, remember 6, and then go to that menu option and choose 4. And you should get 360. If you don't want to go back to the menu, you could press second enter or arrow up and press enter and then just replace the numbers. If you do 11P3, that's how we would say it, 11P3, you should get 990. You know, that should make sense. There are a lot of ways to arrange 11 objects in 3 different ways. You're not choosing them every time, so there's a bunch of ways to do it. And then try 2P2. Let's think about it first. How many different ways are there to arrange 2 objects using both of them each time? Well, I could write my first and last initial as CS or SC. So there are 2 ways to do that. Okay, hey, that is everything I wanted to share with you right now, but I do want to remind you that when you're approaching some of the work in this topic and even in this unit, don't forget to count and look for patterns, especially if all else fails.